Welcome to the week 5 of our calculus course. Last week we learned how to take derivatives using product rule, quotient rule. We learned how to differentiate exponential, logarithmic, and power functions. We even learned chain rule. Now, equipped with all of those rules, we can discover why it is so useful to know the slope of a tangent line to the curve, also known as the derivative of function f of x. Imagine that you are looking at the profile of a mountain. All of those peaks and valleys. How do we figure out what's the highest point at the peak or the lowest valley on the mountain? The derivative of a function f is a very useful tool. On those tops of the mountains and lowest of the valleys, the derivative of the function is equal to 0 or derivative does not exist. So, in order for us to find the location where the mountain reaches its top or hits the valley, what we do is consider all possible input values of x where the function is defined and determine for which values of x derivative is equal to 0 or where derivative does not exist. Those values of x are called critical numbers. Today, we're going to practice finding those critical numbers for different types of functions. If we start with a polynomial, let's say polynomial degree 3, x cubed minus 6x squared plus 9x. How do we determine for which values of x our derivative is going to be equal to 0 or derivative does not exist? Once we have calculated derivative, let's set it equal to 0 and solve the equation. If we factor out 3, we will get, in parentheses, x squared minus 4x plus 3. The product of constant 3 and x squared minus 4x plus 3 is only equal to 0 if x squared minus 4x plus 3 is equal to 0. At this moment, this is a quadratic equation, and we can solve it using two different techniques. We can either observe that we can factor this expression as x minus 1 multiplied by x minus 3, or we can use quadratic formula. The roots x1 and x2 are calculated as minus b plus or minus square root of b squared minus 4ac divided by 2a. For the x squared minus 4x plus 3 equals 0, a is equal to 1, b is equal to minus 4, and c is equal to 3. Using quadratic formula, we will find that x is equal to 4 plus or minus square root of 16 minus 12 divided by 2. 6 divided by 2 is 3. 2 divided by 2 is 1. Those are the same roots that we have found using factoring. On the graph, we can clearly see that the slope of the tangent line evaluated at x equals 1 is equal to 0, and so is the slope of a tangent line at x equals 3. We have the peak at 1 and the valley at x equals 3. Now let's consider a different function where after differentiation we have a derivative written as a fraction. In this particular case, we have a polynomial in numerator and polynomial in denominator. If f of x is equal to natural logarithm of x squared plus 1, its derivative, using derivative of logarithmic function and the chain rule, can be shown to be equal to 2x divided by x squared plus 1. So how do we find the peaks of the mountains and the valleys? Well, we do exactly the same thing as before. We need to check for which values of x derivative of the function f is equal to 0 and for which values of x derivative does not exist. The quotient is equal to 0 only when numerator is equal to 0. Numerator to x is equal to 0 if and only if x is equal to 0. The quotient would not exist if we divide it by 0. In denominator, we have x squared plus 1 equals to 0. This is true if and only if x squared is equal to minus 1. However, none of the squares of the real numbers are equal to minus 1. Therefore, there are no values of x for which derivative of the function natural logarithm of x squared plus 1 does not exist. I also want to take your attention to the function itself, natural logarithm of x squared plus 1. Every function has a domain. It's possible values of x that can be used as an input. Natural logarithm is only defined for the input strictly greater than 0. And we can see that for every value of x, x squared plus 1 would be not only positive, but greater or equal 1, because x squared is always greater or equal 0 for any real number x. So we can see the graph of a function showing that our function natural logarithm of x squared plus 1 is defined for all values of x, and as we predicted, there is only one critical number, x equals to 0. And at x equals 0, derivative is indeed equal to 0. Now let's consider an example where derivative of a function will have exponential function present. For example, x squared times e to the minus x by using differentiation rules such as derivative of a power function, derivative of exponential function, the product rule, and the chain rule, we can show that derivative of this function is equal to 2x times e to the minus x squared times e to the minus x. Because e to the minus x is a factor for both terms, we can factor it out. We can also write e to the minus x as 1 divided by e to the x. Now, in numerator we have 2x minus x squared. We can factor out a common factor x. Our derivative of a function can be written as a quotient, where in numerator we have x and 2 minus x multiplied with each other, and in denominator we have e to the x. Let's find critical numbers. The fraction is equal to 0 if and only if numerator is equal to 0. Those two factors multiplied with each other create 0 only if one of those two factors is equal to 0. So either x is equal to 0 or 2 minus x is equal to 0. So x is equal to 2. The derivative does not exist when the fraction has denominator equal to 0, because division by 0 is undefined. However, exponential function e to the x has always an output strictly positive, so it's never equal to 0. As we can see, there are only two critical numbers. When x is equal to 0, the derivative is equal to 0, and when x is equal to 2, the derivative is equal to 0. Last example is going to have a function, derivative of which contains logarithm. Let's consider function f of x equals x times natural logarithm of x. Using differentiation rules, we can show that derivative of the function f is equal to natural logarithm of x plus 1. The derivative is equal to 0 if natural logarithm of x plus 1 is equal to 0. This only happens when natural logarithm is equal to minus 1. Because natural logarithm has the base e, natural logarithm of x equals minus 1 is the same thing as e raised to the exponent minus 1 equal to x. This gives us a critical number, x equals to 1 divided by e, which is approximately 0.37. Derivative does not exist for all values of x where function is undefined. This is for all values of x less or equal than 0. However, those values of x are not critical numbers, because critical numbers are the values of x which are part of the domain, and our domain contains only strictly positive values of x. So we have a single critical number. When x is equal to 1 over e, derivative at 1 over e is equal to 0. This gives us the value for the function x times natural logarithm of x. As you have seen, solving equations identifying values of x where derivative is equal to 0 or derivative does not exist requires us to know quadratic formula, know how to factor out polynomials, how to use properties of exponential and logarithmic functions. This week in class, we will continue working on finding critical numbers for different types of functions. Until next time.